Hi guys, this is Nitya, Assistant Professor, Department of Mathematics from St. Anne's Arts and Science College. Today we are going to see the bounded sequence and oscillating sequence as well as the theorems and problems based on that. In the last class we had seen the divergent to plus infinity and divergent to minus infinity as well as divergent oscillating sequence we had seen. Today we are going to see the bounded sequence as well as the oscillating depends upon the bounded sequence also we are going to see. Okay. So let us see the first definition. Bounded sequence, bounded above, bounded below and bounded sequence. First, generally we can see what is a bounded sequence. The sequence Sn is said to be bounded if the range of the sequence is bounded above and bounded below. So when we are telling that the sequence should be bounded, it has a range, and in that range the range should be bounded above and bounded below. If it is like that, the sequence is said to be a bounded sequence. So that can be written in a mathematical representation, that is if and only if for m belongs to R. That is, if you are taking any element from the real numbers such that the sequence Sn is less than or equal to m. So the whole sequence which we are taking, that should be less than or equal to m, and where n belongs to also capital R, that is the real numbers. Okay. So this is a bounded sequence definition. You know what is a range, right? In the first unit you had seen that what is a range. That is, if you are taking any function from a to b, that is any mapping from a to b, then the range of the function, that is a subset of b, that is if you are taking the set a and b, and if you are taking some elements in the set b, that should be consistent of all the images of element of a. Okay, it has the image of element of the a. If it is like that, it is a range. Okay, so you know already. So that is a range. Here the range between bounded below and bounded above. So we are mentioning the range in the sequences here. If it is like that, it is a bounded sequence. Okay. So we can see the examples of the bounded sequence now. Before that, we can see what is bounded above and bounded below also. Okay. So bounded above is a sequence is said to be a bounded above if the range is bounded above. That should be upper bound. This also you have learnt in the first unit. Upper bound. What is the upper bound? So the range should be the bounded above. Likewise, bounded below, the range should be a lower bound. You can see the using the examples and it will be easy for us. So bounded below means, suppose if you are taking the example as 1, 2, 3. So which is not bounded but bounded below. Hence lower bound is equal to 1. See the limit here, lower bound is equal to 1. So 1 is a lower bound. So we can say that it is a bounded below. Likewise, for the bounded above, see the sequence minus n. In terms of minus n means minus 1, minus 2, minus 3 and so on. So here the bounded above, upper bound is minus 1 only. Upper bound value is minus 1. So you can start with minus 1 only, that is upper bound. So the sequence is not bounded as well as it is a bounded above. Okay, so it is a bounded below and a bounded above. And we can see the note for that. So all the convergent sequence are bounded. So we know that what is a convergent sequence. Convergence means it has a limit. A sequence which is having the limit is convergent. But they are telling that all convergent sequence are bounded. So whatever the convergent sequence we are taking, that should be a bounded one. And all sequence diverges to infinity and minus infinity, the sequence is not bounded. So yesterday we have seen in the class that is, so if it comes under like that, then it is not bounded. In general, oscillating sequence may or may not be bounded. That we know that oscillating in the sense it never comes under the bounded above or bounded below. So definitely it will not comes under the bounded also. Okay. So now we know that bounded sequence, right? So examples of the bounded sequences, if you are taking the sequences minus 1 the whole power n. So the range lies between minus 1 to 1. Since if we are telling that the bounded sequence, the range should be bounded below and bounded above. Likewise, we are taking minus 1 and 1. So upper bound is 1 and lower bound is minus 1. So obviously it comes under the bounded sequence. The sequence minus 1 the whole power n is comes under the bounded sequence since the range is minus 1 and minus 1. Okay. Now oscillating sequence. Oscillating sequence already we know that it never comes under the any limit. That is the oscillating sequence. It will all oscillates only. the sequence 1, minus 2, 3, minus 4 and so on. It oscillates and it's neither bounded nor bounded below. Okay. So the sequence 1, minus 1, 1, this also oscillates and it is bounded, they are telling. Bounded in the sense it comes under the, because it has a limit as the range is 1 and minus 1. So obviously it is bounded only. Like see the first example, this one. So the same they have given 1, minus 1, 1, minus 1 again, so on. So it oscillates as well as bounded. Okay, girls. Next we can move on to the next example. 1, 2, 1, 3, 1, 4. So it oscillates, but it's not bounded above, it's only bounded below only, because it's we are having the ranges 1, 1, 1, it's there, it's a common. So it's bounded below and but not bounded above, because 2, 3, 4 it's increasing, so it's not comes under the bounded above. So now we can move on to the theorem 22. That is a statement: if the sequence of the real numbers Sn equal to 1 to infinity is a convergent, then it is a bounded. We see the first notice, if it is a convergent, obviously it is a bounded. Now we are going to see using the theorem. Okay, let Sn equal to L. We know that a convergent sequence, it has a limit, so we can use the definition now. So limit Sn equal to L. So by the definition epsilon greater than 0, there exists n belongs to I such that modulus of Sn minus L is less than epsilon. It's the limit of a sequence definition. So basically the convergent sequence has a limit and divergent sequence doesn't have the limit. So we are using the limit of the sequence definition here. Now we are taking epsilon is equal to 1. So modulus of Sn minus L is less than 1. So to prove Sn is a bounded, then we know that as per the bounded definition, modulus of Sn is less than or equal to m. So we have to prove modulus of Sn is less than or equal to m. Okay, so modulus of Sn, modulus of Sn can be written as Sn plus L minus L. So it can be written as modulus of Sn minus L plus L. We know that that is we have taken here as modulus of Sn minus L is epsilon 1. So which is less than 1 plus modulus of L. Now we are going to take the maximum, because we are going to prove that it is a bounded sequence. So we are going to take the maximum of the sequence values. So maximum of S1, S2, S3 and Sn minus 1. So the sequence Sn less than m plus 1 plus L. That is m plus 1 in the sense which we have taken in the bounded sequence definition. See that bounded sequence definition is the range should not be bounded, the range should be bounded above and bounded below if and only if what they have given, we can take the m belongs to R such that modulus of Sn, that is the sequence Sn is less than or equal to m. So that we have taken now. Okay girls, that only we wrote here. So modulus of Sn is less than m, since hence Sn is a bounded sequence. So it can be written as which is less than m plus 1 plus L. So which is less than m obviously. So Sn is a bounded sequence. So therefore the convergent sequence is a bounded sequence we have proved. We can move on to the second one. So second one is problems. This is a problem. The sequence Sn where Sn equal to root n, which is not bounded, for which limit Sn by n equal to 0. So we are taking the sequence as root n, which is not bounded. We are going to prove that it is not bounded, where when Sn by n, if you are applying the limit when Sn by n equal to 0. So you can see the solution, let Sn equal to root n, where n is from 1, 2, 3 up to infinity. So obviously the range is 1, root 2, root 3 and then 4, root 5 etc. and so on, which is not bounded above. So it is not bounded. It is not bound because it's increasing sequence, it is not bounded. So limit n tends to infinity, Sn by n equal to limit Sn value should be root n. So root n by n. So it can be written as limit n tends to infinity 1 by root n. Okay, root n by n can be written as 1 by root n. Therefore, it can be written as, if you are applying infinity, 1 by infinity, which is equal to 0. So Sn by n is equal to 0. So what is the question they have given? Sn by n equal to 0 we have to prove. So we have proved that. Next question. prove that if the sequence of real numbers Sn equal diverges to infinity, then minus Sn diverges to minus infinity. So if you are taking the sequence diverges to infinity, then minus of that sequence should be diverges to minus infinity. So we know that the definition of diverges to infinity and diverges to minus infinity in the last class, right? So if they are taking the sequence Sn diverges to infinity, so limit Sn equal to infinity. So for any real numbers, as per the definition m greater than 0, there exists a positive integer n belongs to I, such that Sn greater than or equal to m and n is greater than or equal to m as per the definition. So minus Sn is less than or equal to minus m, we can write like this. So minus Sn diverges to minus infinity. So limit n tends to infinity, minus Sn equal to minus infinity. Therefore, limit that is the sequence Sn diverges to minus infinity. If you are taking positive Sn greater than or equal to m, then minus Sn less than or equal to minus m. Next question, suppose Sn converges to 0, prove that minus 1 the whole power n Sn converges to 0. So let us take the sequence converges to 0. We are going to prove that the limit Sn equal to 0. So as per the definition, epsilon greater than 0 n belongs to I, modulus of Sn minus L is epsilon. So Sn minus 0 is less than epsilon. Here they have given Sn value is minus 1 the whole power n into Sn minus 0. So minus 1 the whole power into Sn, which is less than epsilon. Therefore, obviously Sn is also less than epsilon, where n greater than or equal to n. Therefore, Sn is minus 1 the whole power Sn minus 0, which is less than epsilon. Therefore, this converges to 0 because it has a limit up to 0. Okay guys, so today we have seen bounded sequence and oscillating in the bounded sequence, examples as well as some theorems based on that, as well as problems. So just watch it. If you have doubts, just WhatsApp me. Okay girls, thank you.